Hi everyone, so this video is going to be about the oxidation reduction of alkynes. This is the second video in the alkyne note series, and if you haven't done so already, I recommend watching the first video, and then also at this point you can get started on the alkyne practice problems that are posted. So first I'm going to talk about the reduction, and then later in the video I'll talk about oxidation. And so as a reminder, the reduction of an alkyne would involve forming more CH bonds, and then fewer CC bonds. And so if we take a look at the structure of an alkyne, we know that we have a triple bond between those two carbons. And then each of those carbons is then bonded to something else. So I'll just draw lines for that. So if we reduce an alkyne to an alkene, then we're adding on a hydrogen to each of those carbons. And then if we reduce that alkene further to an alkane, then we would get two hydrogens that are added to each carbon, and then the remaining or the original bonds. And one thing that I want to point out with alkenes is that we could either get that those hydrogens are added to the same side of the double bond as in the one that I already drew, or we could get where the hydrogens are added to opposite sides and the original bonds are also opposite. And so this the difference between these would be that the first one is cis addition, while the second one would be trans addition. That distinction doesn't matter for alkanes because we're adding two hydrogens total. And so it doesn't really matter how we added them. We're basically just adding two. So we don't even have a stereogenic center in the first place to worry about whether it's cis or trans. The other thing I want to point out is that alkynes are very reactive and more reactive than alkenes. And because of that, we can't really reduce an alkene without reducing an alkyne as well. So let's say that we have a structure like this, where we have a double bond, and then somewhere else in the molecule, we have an alkyne. And so we have two functional groups here. We have the alkyne and the alkene. So there's not really a good way to selectively reduce this alkene. And none of the reactions that we'll talk about here will be able to selectively reduce just the alkene. Can selectively reduce alkynes since they're more reactive. So we can use a weaker reagent to reduce the alkyne down to the alkene without affecting an existing alkenes within the structure. The other thing I want to quickly mention is that none of the reagents that we're talking about here will be able to reduce double bonds within aromatic systems. And so let's say that we're looking at this reagent here, where we have an aromatic system within this ring, and then we also have this triple bond here. The reagents that we're talking about will not be reduced. We have to use special conditions to affect those aromatic systems because they're less reactive. And so all of the reagents that we have here can be performed without touching these ring systems, which is really useful because a lot of molecules have those ring systems. All right, so with that, let's get into the different types of reactions that we have. And so for that, I'm going to erase this. And so I'm going to start off with a simple alkene or alkyne here, where I have an internal alkyne. And so we have three different possibilities or different reactions that we could perform. We could either reduce this alkyne to an alkene, and so we could have a trans alkene here. We could have a cis alkene, or we could go all the way down to an alkane. So I'll draw what all those products would look like. And so for each of these, I'll also draw in the hydrogens that we added. So we added one pair of hydrogens to that first one. We also added one pair of hydrogens to that second one, but just in the cis orientation. And then we added two pairs of hydrogens to get all the way down to an alkane. All right, so let's start off with this bottom reaction and talk about the reagent that we could use for this reaction. And so for this one, we can just use the same reaction that we did for the reduction of alkenes to alkanes in the previous chapter. And so we just use hydrogen gas on palladium. And so since alkynes are more reactive, that alkyne will be reduced to an alkene. And then that reagent is also strong enough to reduce the alkene down to the alkane. And then the solvent usually used for this reaction is something like ethanol. So you might see ethanol within the reagents for this. And so that's how we go from the alkyne to the alkane, exactly the same as what we did with alkenes to alkanes in the previous chapter. Next, we can talk about the cis alkene. And so as a reminder, this reagent here, the H2 on palladium or palladium on carbon, that involves the cis addition of the two hydrogens. And so we can use the same reagent or close to the same reagent where we use the hydrogen gas, but instead of using palladium on carbon, we use something called Lindlar's catalyst, which is a little bit less reactive than the palladium on carbon. And so because it's less reactive, it will react with the more reactive alkyne, but then it'll stop at the cis addition of the alkene and not continue down to the alkane. And so in that way, we can be selective about reducing down to the cis alkene. And so again, the key word for this is Lindlar's catalyst here. All right. For the transalkene, we have to use a different method. The hydrogen gas doesn't work because that would be the cis addition. And so instead of doing the hydrogen gas, we instead use ammonia in the presence of sodium. And so with this, we would get the anti-addition of the two hydrogens. And we're using the sodium with the ammonia. And this reaction is a radical dependent reaction. So I'm not going to show the mechanism here because most organic classes haven't covered radical reactions at this point yet. But I'll post a separate video that goes through the mechanism for this reaction if you're interested. All right, so altogether for this chapter, for the most part, what you want to remember is what reagents will stop the reaction at the alkenes, and then how to get a selective trans or cis alkene depending on what product you want. And then the bottom one down to the alkane is a review of that same reaction that you did with the alkenes. All right, with that, let's move on to oxidation. And so with oxidation, we have two reactions that we're going to talk about. We're going to talk about hydroboration oxidation, and then we're going to talk about acid-catalyzed hydration. And before I do that, I want to talk about two different types of alkynes that we have, because this will be really important for predicting products for reactions. So we could have two possible alkynes. We could either have a terminal alkyne, which has a hydrogen on one side of the carbons. And then we could also have a internal alkyne, which has no hydrogens bonded to either of the carbons. And so why this matters is because the first one ends up being asymmetric. We have one of the carbons is more substituted. So in this case, this left one is more substituted than the other carbon in that alkyne. However, in the internal alkyne, we actually end up seeing that both carbons are equally substituted, since neither of them have hydrogens. And so because they're equally substituted products, this will matter because for a terminal alkyne, we will have that the reactions are selective towards a carbon, while for the other alkyne, the internal alkyne, they're equally substituted, and so we won't have selectivity, and we'll get a mixture of products. And this will be true for both of the reactions. And so the key difference between hydroboration and oxidation or acid-catalyzed hydration is that we will get a different selective product for the terminal alkyne, but we will get the same mixture of products for internal alkyne. And so for the internal alkyne, either of the reagents will give you the same two products. And I'll show what those will look like next. All right, so let's start off with hydroboration oxidation. And so for this one, what we're looking at, and this is kind of a review of the alkene oxidation, is that we're going to follow anti-Markovnikov's rule, where it's substituted carbon. And so if we were to take this alkyne, or this terminal alkyne, and react it with the boron reagent followed by base and peroxide, we would get the formation of what's called an eno, where that OH goes to the less substituted carbon. And so we can see that this highlighted region right here is what is called the eno. And so this technically is a product of this reaction. However, this enol can undergo a process called base-catalyzed tautomerization, where the equilibrium leans towards the aldehyde product. And so the final product is something like this, where we have a aldehyde due to the keto form of this tautomerization process. And the reason it's base catalyzed is because you can see that in the second step of the reaction, we have hydroxide. And so this process is going to be base catalyzed. There's also for the second reaction, and I'm going to post a video that goes through the mechanism for this step. It's relevant for a lot of different chapters, so it's not just important for alkynes, but I'll link it below if you're interested in the mechanism for this process. All right, so we have that this reaction yields the keto form, and for a terminal alkyne, we get an aldehyde here. Okay, so let's say that we did this reaction, but what I'm going to do here is I'm going to add an extra carbon here on the end. And so now we have an internal alkyne. Then if we do this reaction, we don't get a selectivity because now we have equally substituted carbons. And so what this is going to look like is something like this, where we get that the eno could either form, so that double bond is going to stay at the same place, but we could get that the OH adds to this carbon, or it could add to this carbon down here. And so both of those carbons are in the same position as where the alkyne was within the chain, but that OH placement could be different. And so these two products can also undergo base-catalyzed tautomerization. And so the equilibrium product of this reaction will be the ketone forms of these two reagents. Now just slide these over so I have space. All right, so after we undergo that base-catalyzed tautomerization, that alkene turns into an alkane, and we get a ketone for the tautomer, or for the keto form. And so in comparison to a terminal alkyne where we got an aldehyde, here we get ketones, and we get a mixture of products. And so as a review, an internal alkyne leads to a mix of products, and both of them will be ketone products, while a terminal alkyne leads to an aldehyde. and we only get that one aldehyde product. We don't get the other product because we have anti-Markovnikov's, we follow anti-Markovnikov's rule for the first step. All right, so with that, that wraps up the hydroboration oxidation, and then we can move on to acid-catalyzed hydration. And for this, I'm just going to, or no, I'll just redraw them. So here, for this reaction, we're going to see something really, really similar, except that first reaction is going to be a little bit different. And so what I'm going to do is take this first reaction and substitute out the reagent. And so for this reagent, we're going to use sulfuric acid or another strong acid in the presence of this mercury-based reagent. And so for this, we're also going to get an enol. However, now we're following Markovnikov's rule. And so the alcohol goes to the more substituted carbon. And so we get a enol that is located internally. And then this, in turn, can undergo acid-catalyzed tautomerization. And so the reason it's acid-catalyzed this time, have acid in the solution. We have the H2SO4. And so for this one, we undergo acid-catalyzed tautomerization. And again, the video linked below is going to go through the mechanism for base-catalyzed versus acid-catalyzed and compare the two different steps within the reactions. All right, so after we undergo that tautomerization, we end up with a ketone in this one. And so our final product will be that ketone that's internal. And so altogether, what we get is that a terminal alkyne yields a single product, which is a ketone. In comparison to that, if we were to take the same reagent as above here and undergo that same reaction, and what you'll notice is what I'm going to do is just copy this exact same reaction here and change just a few things around. And that's because this reaction will give us basically no selectivity because we have an equally substituted carbon. So I'm going to substitute out the reagent that we're using to make it that H2O in the presence of sulfuric acid and the mercury-based reagent. And in that first step, we're going to get the exact same intermediates that we got from the hydroboration oxidation. And then instead of base-catalyzed tautomerization, we're going to have acid-catalyzed tautomerization. And we're going to get the exact same products that we did with the hydroboration oxidation. And so what that means is that an internal alkyne will also give a mixture of products that are ketones. And so if we wanted to do this reaction with the internal alkyne, it doesn't matter what reagent you use, you will still get a mixture of products, and you'd have to do some purification steps to isolate only one of the products. All right, so if we compare and contrast hydroboration oxidation with acid-catalyzed hydration, the key difference between the two reactions is whether you're doing a terminal alkyne or an internal alkyne, and then also whether you get acid-catalyzed tautomerization or base-catalyzed. In the case of hydroboration oxidation, you get base-catalyzed. I think of hydroboration, B, base, catalyzed tautomerization, versus acid-catalyzed, you get acid-catalyzed tautomerization. All right, but both of these go through that enol that then gets converted to a ketone form, and you only get a single product if you have a terminal alkyne. Otherwise, if you're working with an internal alkyne, you get a mixture of products that are both ketones. All right, that wraps up this video, and I'll see you in the next one.